Hi guys, welcome to our video for 6.6. Today we're going to be working on finding all the zeros, or in other words, all the x-intercepts of a polynomial function. And our goal with this is to get closer to being able to graph a polynomial function. We've talked about end behavior earlier on this chapter. And if we can also find all the x-intercepts, that gives us one more piece of information that we can use to actually graph the polynomial function itself. So take a moment to set up your note sheet with the section, the date, and the I can statement, and then resume the video. All right, so we're going to start today by looking at two theorems. And these are important for you to know because they kind of give us the underlying foundation for the information we're going to use to find our zeros of polynomial functions. And the first theorem is called the factor theorem. And the factor theorem says, let f be a polynomial function, so any polynomial function, then some factor x minus c is a factor of f of x if and only if f of c equals 0. And what that's really telling you is that you can know if something is a factor. In other words, if x minus c is the actual factor of a polynomial function, if and only if, when you put in that value for f, you end up with a result of 0. In other words, you end up with a remainder of 0 when you do synthetic division. So this theorem, which can be proved through a longer proof, basically is telling you what you already know. It's just justifying it. That if we have a remainder of 0, then x minus c can be guaranteed to be a factor of f of x. The other theorem that we're going to be relying on today, and this one is particularly important, so I really want you to pay close attention to this one. The theorem is called the number of zeros theorem, and it tells you that a polynomial function has exactly as many zeros as its degree. And this is really important because it gives us an upper limit on how many zeros we need to look for. And tells us that when we're searching for zeros, we have to continue until we get exactly as many zeros as the degree. Now, an important corollary to this is that a polynomial function may not have as many real zeros as its degree. Because a polynomial function might have it has to have as many zeros as its degree, but not all of them have to be real. Some of them may be imaginary, which we'll see as we continue to work through this chapter. So it's totally possible that you might have fewer real zeros than the degree, but we know for sure that as an upper limit, we cannot have more real zeros than the degree. So once we find enough zeros, we know we can stop looking for them. So our goal here is basically, the goal of 6.6 is to be able to answer a question like this. I want to find all the real zeros, in other words, all the x-intercepts of the function f of x equals 2x cubed plus 4x squared minus 11x plus 5. That's our goal. And we could initially start with trying to use some factoring techniques, like we looked at earlier this chapter, but most polynomials don't factor. There's really only a very few instances where they do in the broad infinity of possible polynomial functions. So we need some techniques that don't rely on factoring. And basically, our goal here is to use yet another theorem in order to start coming up with what the possibilities are for zeros for this. Because what we looked at last section is that you can use synthetic division to check numbers, right? You can do synthetic division with different possible values to see if they are in fact zeros. But we don't want to just have to guess at infinity possible numbers. We need some way of narrowing that down so that we have just a few numbers to guess from rather than infinity numbers, and then we can guess and check with synthetic division. And the rational zeros theorem is what helps us do that. So the rational zeros theorem says that for a polynomial function, the possible rational zeros can be found by writing all the ratios p over q plus or n minus, where p is a factor of the constant term, in other words, the last term, and q is a factor of the leading coefficient. So, for example, if we look at our example up here, the f of x example, the p value is 5 because that's the constant term, and the q value is 2 because that's the leading coefficient. And so if we wanted to use this plus or minus p over q technique to list all the possible zeros of f of x, and this is not all the zeros, it's just the possibilities for us to guess from. What we're going to do is we're looking at the factors. So in other words, the factors of q would be 1 and 2. And the factors of p would be 1 and 5 in this case. So if we wanted to list all the possible zeros, it's p over q, and it's plus or minus. So for example, if I start with 5 as the p-value, I would have plus or minus 5 over 1, plus or minus 5 over 2. And then we'd also have plus or minus 1 over 1 and plus or minus 1 over 2. These are all the different options that come from plus or minus p over q. Now, just to make this a little bit cleaner, I'd probably write this as plus or minus 5, plus or minus 5 halves, plus or minus 1, and plus or minus 1 half. So really, I've got 8 possibilities that I need to guess from. And we know that at most, we could only have 3 possible zeros for this function, and we may even have less than that, because some of them might be imaginary. But we can use synthetic division to check our 8 possibilities and see which one of them actually are zeros for this polynomial. So let's look at another example of this. Let's say I ask you, okay, I just want you to list for me all the possible zeros of this polynomial, f of x equals 6x to the 6 minus 7x cubed minus 25x squared minus 9. So our p-value is 9, and our q-value is 6. So when I think about the factors of 6 are 1, 2, 3, and 6. The factors of 9 are 1, 3, and 9. So I need to list out all the possible p plus or minus p over q values. And so I'm going to try to do this in a fairly systematic way. I would start with the 1 for p and do all the different q options, and then the 3 for p and do all the different q options. And then I would do the 9 for p after that, and again, do all the different q options. So let's see if we can make a list here. So we've got plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, and plus or minus 1 over 6. And then we've got the same thing here for the 3. So again, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 3, and plus or minus 3 over 6. And then same thing for 9. So plus or minus 9 over 1, plus or minus 9 over 2, plus or minus 9 over 3, and plus or minus 9 over 6. So it looks like we've got 24 different possibilities here, but the next thing we have to do is look for duplicates, because some of these match up. For example, plus or minus 1 over 1 is the same thing as plus or minus 3 over 3, so I'm just going to cross out the 3 over 3. Also, plus or minus 1 half is the same thing as plus or minus 3 over 6. And similarly, we've got plus or minus 3 over 1. That's the same thing as plus or minus 9 over 3. And we've also got plus or minus 3 over 2, which is the same thing as plus or minus 9 over 6. So I'm able to rule out some of these. So if we take this and just summarize our list, we've actually got plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 3, plus or minus 3/2, plus or minus 9, and plus or minus 9/2. So in total here, we've actually got 16 possibilities for real zeros. And we know that there are at most 6 real zeros and possibly less if some of them are imaginary. So it seems like this is a lot of guess and check, and it sort of is. I mean, 16 possibilities is a lot. However, given that before this we had infinite possibilities to guess and check from, we've ruled it down quite a bit. We've gone from infinite possibilities to 16, which seems much more manageable. So let's do a final example where we take this all the way through the process. So if we want to find all the real zeros of this function, 2x cubed plus 11x squared minus 7x minus 6, we're going to go through the different steps to do this. So the first step, step 1, is find all possible zeros. And that's using plus or minus p over q. So we're going to do that first. We're going to find all the possibilities. We know that p is 6 and q is 2. So our factors for 2 would be 1 and 2. And our factors for 6 would be 1, 2, 3, and 6. So our possibilities here, we've got a fair number of them. So I'm going to go through each one. So plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 3 over 1, plus or minus 3 over 2, and plus or minus 6 over 1, and plus or minus 6 over 2. Now, some of these are duplicates, right? We've got 1 over 1, which is the same thing as 2 over 2. We've also got 6 over 2, which is the same thing as 3 over 1. So we can rule those ones out. So I'm just going to rewrite this here. So I've got plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 3, plus or minus 3/2, and plus or minus 6. So we've got in total 12 possibilities, which is not too bad. It gives us a limited number of things to guess from. So that's step 1, find all the possible zeros. Now, step 2 is we're going to use synthetic division to find real zeros. And we may just find one or several using synthetic division. And the basic idea here is we're just going to guess from our possibilities. And you can kind of start wherever you would like to start. So for example, maybe I think, hey, you know what? I think 2 is going to be a 0 for this. So I would try it with 2. So I would do 2 as my synthetic division. Then my coefficients are 2, 11, negative 7, and negative 6. So I guess I don't need the comma here. 2, 11, negative 7, negative 6. And we're just going to go through the synthetic division. So I drop the 2. 2 times 2 is 4. 4 plus 11 is 15. 2 times 15 is 30. Add those together and you end up with negative 23. Times 2 is negative 46. And I come up with a remainder of negative 52. So that tells me that 2 is not a possibility. 2 is a bust. So let's try another one. Let's try 1 this time. You're essentially just guessing and checking, so you can pick whichever ones you want. So I'm going to try 1. 2, 11, -7, and -6. And if I drop that down, so bring down the 2, 2 times 1 is 2, 11 plus 2 is 13, times 1 is still 13, -7 plus 13 is 6, 6 times 1 is 6, -6 plus 6 is 0, so we have a remainder of 0. So that's great. My second guess was successful. 1 is one of our possible zeros. And at this point, we're down to just a quadratic remaining. Our remaining quadratic here is 2x squared plus 13x plus 6. So step 3 in this case is solve quadratic for the last 2 zeros. Now, sometimes if it's more than a cubic function, you may need to do the guess and check multiple times to get down to the quadratic. In this case, though, we only had 1, because we've got 2x squared plus 13x plus 6 equals 0. That's our quadratic function for this problem, right? And we can solve this numerous different ways. You could use the quadratic formula, you could factor it, whatever you prefer, right? In this case, just as for a bit of review, why don't we use the factoring technique? We'll use the split method. So if I wanted to use the split method here, I'd be looking for factors of 12, because 6 plus 2 is 12, that add up to 13. And right away I would see that my factors are 12 and 1. So I could split this, so 2x squared plus 12x plus x plus 6 equals 0. And then factor each part in pieces, so 2x times x plus 6 plus x plus 6 is already here in this case, and x plus 6 share no factors. So now I can just factor out the x plus 6, and I've got x plus 6 multiplied by 2x plus 1 equals 0. And this tells us that our other 2 zeros are x equals -6 and x equals -1/2. So we have 3 zeros for this problem. We've got x equals 6, x equals -1/2, and then from our initial synthetic division, we also know that x equals 1. And that gives us the 3 zeros for our original function, or our original polynomial. So that brings us to the end of our video for 6.6. Basically, the final example here is going through the entire process to find the zeros for a cubic polynomial function.